What's that? Okay, so I'm going to test the audio on YouTube now.
I can hear that, James.
Chris, can you speak?
Yes, 1, 2, 3, testing. Yep. And I can hear everyone clearly.
Josh?
Yeah, this is all good. It's coming through on the YouTube as well.
Welcome everyone to the Hibiscus Coast Astronomical Society meeting. As you've got the message, we're doing it online today, just until we go down to level 1. So the next meeting should probably be an in-person meeting again, but just keep checking your Facebook group and the email, and we will definitely be letting you know what's going on there. So this evening, first off, we're going to have a chat to Josh, who'll be telling us about the news, all the excitement about Mars, and then we'll be popping over to Chris, who'll be talking about the history and importance of X-ray astronomy. It's radio astronomy. So very interesting topic, especially for people like me, like radio astronomy. But there we go. As you might have seen in the previous email as well, our AGM, annual general meeting, is going to be postponed by a month. That's pretty much just because of where we are right now, and we need to get some prep work done for that. So it'll probably be in April. So keep an eye out for that. We're looking for other people who'd like to join the committee. It's one meeting a month. We just come in a bit earlier, and your assistance is quite valuable with that. For those of you who joined earlier, you would have heard we've got a new music theme in the beginning. Unfortunately, I couldn't play it all the way through to the end, and thanks to Josh for making that possible. He actually composed, wrote and produced the whole thing. So there we go. You'll hear it at the next meeting, I'm sure. Anyway, let me get Josh up here. Okay, and if you give me 1 second.
Looks like I can't share my screen.
Okay, Chris, you need to do the share the screen settings.
You can get that message, host disable participant screen
sharing.
Yeah,
that's correct, Chris. If you're there, you need to enable screen sharing. And you're on mute as well.
Just sorting out some technical issues here, everyone. Thanks for bearing with us. Okay, looks like I can share my screen now.
Okay.
Great. Okay, cool. I think we're ready to go. Thanks, Chris. You can turn off your video again now if you want. I think we should be good to start. Okay, yeah, thanks everyone for joining us. This is the first virtual talk we've done for a while. So we were getting quite good at doing these back during the lockdown. And obviously with the surprise lockdown, we thought we'd roll this out again. But as you can tell from the technical hiccups, we're a bit rusty, a few things to sort out, but I think we're all good to go now. So let's have a look at what's been happening above us with the news. So recently there's been a lot of news about Mars. There's a lot of Mars missions happening at the moment. So I thought for tonight's news segment, we'd kind of focus on all the various Mars missions. Excuse me, I'll just close my door because I'm getting a bit of feedback from the sound. Okay, that's better. So, what's been happening with Mars? So first in the news, we've had the United Arab Emirates HOPE probe has entered the Mars orbit. So this is the UAE branching out into the kind of space exploration field. And this probe, which is called HOPE, recently entered the orbit of Mars. So this was launched last year, 19th of July, and it reached Mars 9th of February, so about a week and a half ago. The plan for the UAE HOPE probe is to study the daily and seasonal weather cycles on Mars, so we can find out more about what's going on there, and also to look at things like some of the biosignatures of what's on Mars. So the UAE Space Agency itself is relatively new. It was created in 2014. So only, 7 years in, and they've already launched a probe to Mars. And that's quite impressive because statistically, when we look at all of the various missions to Mars by NASA, the Soviets, everyone, things tend to go wrong. So statistically, about half of Mars missions fail. So it's quite impressive that the UAE has managed to send HOPE to where it is. Also, China's Tianwen-1 arrives in Mars orbit. So this was launched last year, also in July 23rd, and this reached Mars a day after HOPE, so on the 10th of February. And the probe here actually has a lander rover, which is going to touch down on Mars and explore Mars's surface. Now, China's not always forthcoming with details of the exact dates of when this is happening, so we're pretty sure this is going to happen around May, but we don't know the exact date yet. So stay tuned to find out what's happening there with this rover. This is China's second attempt at a Mars mission. Its first attempt was in November 2011, when they tried to piggy bank off a Russian mission called Phobos Grunt, which is going to go to one of Mars's moons. But that mission failed to leave Earth's orbit, and as a consequence, China's contribution to that mission also failed. So this is their second attempt at getting to Mars, and this time they've done it. So you might be wondering, who's been to Mars with all these new missions going on and what's been in the past? Well, there are now 6 countries or 6 entities that have sent space exploration missions to Mars. So United States, obviously, Soviet Union, the European Space Agency, or ESA, India, and now just in the last couple of weeks, the UAE and China joining those ranks. So you can see that Mars is starting to get quite busy with everything that's going on. But there's still one more thing happening very soon, and that's NASA's Perseverance rover. So the probe carrying this reached Mars a while ago. It's been in orbit, but the big news is that it's now planning to land on Mars. And this is going to happen within the next 12 hours, I believe, just checking my clock. Yeah, about, I think, 12 hours from now. So again, this was launched July last year, July 30th, 2020, and it arrives at our time, 19th of February, so it's tomorrow. The rover is a car-sized rover. It's about 3 meters long, 2.7 meters wide, and 2.2 meters tall. And a lot of the design of this is based off the predecessor, Curiosity. So obviously there's some updated technology and all kinds of new whiz-bang gadgets. But NASA said that design, which we know works. And the plan is to investigate astrobiologically relevant ancient environment. So that's quite a mouthful. But basically, it's trying to look for possible signs of life or things that might be relevant to life. And its nickname is Percy. So the NASA people working on it, for short for Perseverance, they call it Percy. Now, here's a diagram with some of the equipment that's on the rover itself. I'm not going to go into detail with all the different things here, but you can see there's lots of different gadgets and gizmos, and quite a few from other countries as well. So in some ways, this is kind of an international effort with what's going on here. And when it lands on Mars tomorrow morning, that descent has been nicknamed the 7 minutes of terror. So they call it that because it takes around 7 minutes to get from the outside of Mars's atmosphere all the way down to the surface. And during that time, there's a lot of things that can go wrong. So everything has to go right tomorrow during the 7 minutes of terror for this to all land and hang together. So as you can see from this diagram, it will separate from the top bit and then enter the atmosphere, start to decelerate, and then it deploys the parachute when it's at an altitude of around 10 to 30 kilometers up. And at this stage, it's traveling at a velocity of 1,500 kilometers per hour. So it's really fast. A bit later, there's heat shield separation, and then the radar lock, and then something called the terrain relative navigation solution. So this is something which is still quite new, and basically the actual craft itself is going to use lasers to scan the surface of Mars and try to map it out. So as it's descending, it's creating a real-time image of where the hills are and where the flat parts are. And as you can see, as it descends, the velocity will be decreasing, it's slowing down. And then finally, the back shell separation, a powered descent, and then the actual rover itself will be dropped down by a sky crane. So yeah, if everything goes well, it takes about 7 minutes from the atmosphere down here, and this will be happening tomorrow morning. So if you're keen to watch this, head to this website here, or just Google Mars NASA Watch Online, and you'll find some links there to various live streams that will be happening. Now, I've converted some of these times to New Zealand time. Hopefully I got it right. So in my calculations, at 7 a.m. tomorrow, the NASA webcast should begin. And then at 8:15, there's a live landing broadcast will start. And the actual landing is scheduled to happen at 9:55, so just before 10 a.m. our time. So if you happen to be around and near a computer close to 10 a.m., see if you can check out this website or just Google Mars NASA Watch Online, and you might have a chance to watch this historic landing of a rover. So you might be wondering, well, why are all these things in Mars happening at once? So all these three missions that I mentioned all launched in July of last year, and they're all reaching Mars around now. And that has something to do with what's called the Earth-Mars conjunction. You see, Earth and Mars obviously are on separate orbits, and they travel at different speeds. So it's kind of like two race cars going around a race car track. Occasionally one will lap the other one, and during those points in time, they're closest together. So when Earth and Mars are closest, we call it opposition. And when they're furthest away, we call it conjunction. And these terms can seem a bit confusing because you might think, well, opposite sounds far away and conjunction sounds close. Why do they call it that way? Well, the whole naming comes from the fact that during an opposition, Mars is on the opposite side of Earth than the Sun. And during a conjunction, when we're looking at it from Earth, it looks like the Sun and Mars are kind of lining up. So that's where the names come from. They're a bit confusing. What this means is during an opposition, or just before, it's the best time for a launch window for Mars missions, because we can take advantage of the fact that things are quite close. And these launch windows happen every 26 months or so. So if we look back, we can see that every time one of these happened, so November 2013, we had some missions that were launched, March 2016, May 2018. So this recent one, July 2020, as we've seen, this saw the launch of UAE Hope, China's Tianwen-1, and NASA's Perseverance. The next Earth-Mars opposition is December 2022. At this stage, there's no confirmed details for missions that are planned, but I'm sure as it gets closer to time, we will hear about more missions that are coming up during that time. And so that's everything that's been happening with Mars. So as you can see, it's quite an active source of news at the moment. So we've got the Hope, the Tianwen, and the Perseverance. If you're around tomorrow, you might want to see if you can watch that live, check that out. And yeah, for now, that's everything for the astronomy news. So now I will pass over to Chris. I'll turn off my cam and
right. I'm here now. See if I can share my screen. Let's bring her up here, guys. Share screen. This looks like me. And if I go to slideshow, play from the start, that's a good enough place to start, isn't it, guys? At the start, beginning. Okay, we're all set. Looks like I'm on, guys. Well, welcome and thank you for joining us. As Josh introduced me, I'm Chris Benton, and I'm going to present to you a topic which I personally find absolutely fascinating, and I'm sure you'll also find it fascinating and very interesting. So let's get going. So I start the talk with this image. It's one of my favorite images in astronomy, and it is taken in X-ray, purely X-ray wavelengths by this telescope here, which is NASA's Chandra X-ray Observatory. And what we're looking at is a supernova remnant. Now, some of you may ask, hey, what is a supernova? What is a supernova remnant? Well, it goes back to massive stars larger than 8 solar masses. In other words, 8 times the mass of our sun. So that's considered a massive star. So any star larger than that, as it ends its life, nuclear fusion at its core stops. It runs out of material to carry forth, doing nuclear fusion and producing energy and heat. So the core collapses. And when the core collapses, 2 things happen. First of all, you get what we call a stellar corpse, a compact, dense, hot object bang in the middle, which can be a neutron star if it's between 8 and 20 solar masses, or more than 20 solar masses, you get a black hole in the center. As that core starts to collapse, suddenly all the outer layers of the star also starts to collapse inward, collapse, and it hits and rebounds off that new compact core object, whether it be a neutron star or just before the black hole forms, it rebounds back out, and all that material starts heading back into the material in outer space surrounding the star, called the interstellar medium, or ISM. And that's what you're looking at here. So if you have a look at this in X-ray wavelengths, there's our neutron star, really hot, burning away in X-ray wavelengths in the middle. And what's going on here, this is all the material, and it's racing out at huge speeds, and it's going wham, 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 constantly into the interstellar medium as it moves out, creating multiple high energy shock waves. And the material is striking the material in outer space, the interstellar material is being struck so hard by the stellar material, it's creating X-rays, and that's what we're seeing here. Look at all the intricate little details and stuff going on. So you can imagine there's a lot of information to astronomers in that image. Why? Because it's taken in X-ray wavelengths. So when I see an image like that, it just begs me, well, who were the very, very clever guys, the pioneers, who first started developing and had the insight to realize, hey guys, if we look at the out in space in X-ray wavelengths, we're going to see a lot more and understand a lot more astronomical objects and processes and so on. So who were these people? How did they do it? And when did they do it? It just begs that question. So to that effect, tonight's talk is titled The History and Importance of X-ray Astronomy, which means we're going to talk about the pioneers, we're going to talk about what various missions they did and what sort of discoveries they made. And it was all pretty made in two crucial decades, the 1960s to the 1970s. Those 2 decades were the important two. And I'm going to do this with 6 chapters, which I'll go through now. And I will mention here, there's some space at the end for any questions, so feel free online to ask any questions, and James or Josh will keep a note of those, and we can have a little discussion afterwards if anyone's got any questions. So just save them to the end. By the way, guys, check out the Astronomical Society's mug. Come to one of the meetings and you can buy these, $15. They're pretty cool. Hibiscus Coast Astronomical Society, where all the cool guys are. There you go. Chapter 2 will be on the 1960s and 1970s, as I mentioned. It really started to get underway in the 1960s, and then we started seeing satellites dedicated to X-rays in the 1970s. I've put asterisks here beside them because this is going to be the focus of my talk, will be those 2 decades. We'll mention briefly about the 1980s and 1990s just to carry it through for you. And then, of course, we'll wrap up with a summary chapter. Okay, so let's have an introduction to X-ray astronomy. Let's talk about the properties of X-rays and how they're important. What sort of processes do they pick up in astronomy? So here's a nice diagram. Hopefully a lot of you already seen that before. And that's the full spectrum going right across of light, what we call light or electromagnetic radiation. And you'll see in the middle here, as you can see, it's a very narrow band that's been expanded here. That's visible light wavelengths. That's the light that we see, that our eyes pick up and that we perceive the world around us. And at this end up here, you've got the high energy gamma rays, which are really high energy, short wavelengths. They're over here, and it goes all the way down to these radio wavelengths, low energy, long wavelength, long wavelength electromagnetic radiation. And here's the X-ray guys right up here. So they're very highly energetic, very short wavelengths, as you'll see here, with high frequencies. So 0.03 to 3 nanometers. That's very, very short wavelengths. The photons are then broken up into 2 groups, into soft X-rays, which are sort of down the lower end, 0.5 to 5 kilo electron volts, and then the hard X-rays, which are between 5 and 30 kilo electron volts. Now, so X-rays that sound very exciting, they're highly energetic, but despite being highly energetic, there's actually a problem with that for astronomers, not so much for us, but down on here on Earth, but for astronomers, is that X-rays do not penetrate very well through Earth's atmosphere. They get absorbed in a zone called the ionization zone, where the X-rays get absorbed as they ionize atoms high up in the atmosphere, such that these sort of lower energy soft X-rays, they penetrate only down to about 150 to 200 kilometer altitudes. So if you go down to say 100, 120 kilometers, or go up rather to that altitude, you don't see much in the way of soft X-rays. And interesting enough, that's where most of the X-rays coming from cosmic origin, in other words, outside the solar system, they are usually soft X-rays in that lower energy range. So you don't get to see them unless you can get altitudes of 150 to 200 kilometers and above. So it makes sense from there that in actual fact, X-ray astronomy never really took off until the space age, and then get above the atmosphere. You'll make a note here that the hard X-rays, the higher energetic ones, because they have got higher energy, they can actually penetrate down to about 40 kilometers, at an altitude of 40 kilometers. Okay, so that's a little bit about X-rays and where they fit into the scheme of things. How about the importance of X-rays in astronomy? It's usually high energy processes and events that create these high energy photons or radiation. Within the solar system, the two main sources are solar flares from the sun, are prominent in X-ray, and also the aura around Jupiter. So charged particles come in from the sun. Jupiter's got some very strong magnetic field lines, and it directs them down towards the poles of Jupiter, pretty much like the auroras that you get on Earth, except the Jupiter ones, a lot more powerful, and they emit in X-ray wavelengths. So beyond the solar system, yet we call those cosmic X-rays. There are multiple sources and processes that can generate them. And I've just named a few here just to go over with you. So first of all, thermal radiation. That refers to the how hot an object is, how much kinetic energy is going on in its surface, generating X-rays. So neutron stars are a classic. You saw one in that very first image of Cassiopeia A, supernova remnant. The temperature on the surface of neutron stars can be up to 1,000,000 degrees Kelvin. At those sort of levels, don't worry about whether it's Kelvin or Celsius. It's pretty much all the same at those temperatures. So they've got very hot surfaces. Their surfaces radiate in X-rays. So that's a good enough reason to be wanting to have a look and investigate neutron stars more. Another process called Bremsstrahlung radiation. And that's where you get hot gases in what we call the intergalactic medium. So a lot of galaxies are all bunched together, gravitationally bound in what they call galaxy clusters. And between the individual galaxies, you get a lot of gas sitting in there, and the gas is moving around at high velocity. And if you get yourself a nucleus of an atom here, you get a high-speed electron coming in like this, and as it gets deflected off the side of that nucleus of an atom and gets deaccelerated in this direction, it gives off energy in the form of X-rays as it decelerates. And that's called Bremsstrahlung radiation. So if they can identify that in X-rays, they can identify it gives an idea of the temperature, in other words, how hot or how fast are the gases going on in that galaxy cluster. And they can also gives them an indication of the composition of those gases as well. What sort of atoms are up there? Synchrotron radiation. That's a form of radiation that's generated by charged particles spiraling around strong magnetic field lines. And there are a lot of objects out there in space that have very strong magnetic field lines going around them or going out from them. And if you get high energy, high velocity, charged particles, typically electrons, that are spiraling round and round and round as they travel through that or around that magnetic field line, that will give off radiation. And some of that radiation is often given out in X-rays. And identifying the type of radiation in X-rays, they can then get information on the magnetic field strength and the direction of those magnetic field lines, which in turn gives you more information about the object from where those magnetic field lines are coming. There's another process called inverse Compton scattering, and that's where you get what they call relativistic, in other words, charged particles traveling close to the speed of light, such as an electron, and you might say, whoa, where would have that charged particle come from? Often one of those supernova explosions that will quite happily give out charged particles traveling close to the speed of light. And if one of these electrons, charged particles, comes traveling along really, really quickly, and it happens to collide with a low energy photon in space, and typically microwave photons from the cosmic microwave background, they are low energy photons of light that are permeating through the entire universe right now. We're bathing in them, essentially. They're everywhere. And if you get an electron that strikes one of those photons, it imparts its energy to that low energy photon and creates a high energy X-ray. So they can get a lot of information from that as well about what charged particles are doing and how fast they're going in which direction. So you can clearly see that X-rays play an important role in studying objects and various high energy processes going on in astronomy. So how does it get all underway? So let's look in the 1960s at the very early X-ray astronomy. We're going to look at Geiger counters and proportional counters. We're going to talk about sounding rockets and balloons, and then we're going to talk about these three giants of astronomy. So you might think, well, how on earth in those early days would they have captured and counted these high energy photons, X-rays? Because, you know, you think about it, if you just put up a plain mirror, they're so energetic, they will go straight through a mirror. There's no point in putting a mirror face on to try and catch these guys. So what they did is they used Geiger counters, what we use on Earth to measure radioactivity. So essentially what you've got here is a sealed metal tube, and they fill it up with a gas, typically an inert gas such as argon and xenon. They then put a filter window over here that is designed to allow only X-rays of a certain range of wavelengths through it. And only those photons of that within that range of energies can get through that filter window and go in here. What happens is then those X-rays get in here, they collide with those atoms, they ionize them, which means boot an electron off them. The electron then gets attracted to they put a wire in here, a positively charged wire, or essentially acts as an anode, and that attracts, the electrons get attracted to there, and that completes an electrical circuit around through here. And what they do is they put a detector on here that is able to measure the current and hence count from there, count the number of photons of the X-rays in that range that the window let through. And that's how they started picking them up. So that's all very well, but soon it gets a little bit frustrating because it only tells you the number of photons that you're counting, you know, in that entire range. You'd like to differentiate them maybe between that range. And that's when they created the proportional counters, whereby they are able to amplify the electron numbers and energy levels proportional to the photons of different energy levels. So for example, if you've got a range yay big, photons fitting within that sort of energy range cause a lot of amplification of numbers of electrons, maybe the mid-range ones, a medium amount of amplification, and the lower ones, less amplification. And that enabled them to differentiate the amount of photons splitting up into groups within that range which the filter would let in. So that was a very clever little thing that they came up with also in the 1960s. So moving on now, so these sounding rockets. So sounding rockets, you might say, what are they? That just means suborbital flights. Instead of a rocket going up in orbit around the Earth, the rocket comes up like that, just goes up for a suborbit and then goes back down again. And they're called sounding rockets. And they also use balloons. And it was this guy here is pretty much considered the grandfather of X-ray astronomy, Herbert Friedman. And from 1949 onwards, but mainly right throughout the 1950s, he got himself a lot of captured German V2 rockets from the Second World War. These guys went out up to an altitude of about 150 kilometers. So you could see they were quite happily able to detect the higher energy X-ray photons. But they had with them Geiger counters, which were 1 by 1 centimeters. In other words, yay big. That's the technology would allow them at the time. 1 by 1 centimeter Geiger counters. They were able to pick up some weak X-ray signals coming from the sun, obviously because the sun's a lot closer. So after that, the general sort of thought and consensus in the astronomical society was the only reason we are picking up these X-ray signals from the sun is because the sun's close proximity. That's the only reason. And the rest of the cosmos is just so far away from us. There's no point in even looking or going there. Let's just be happy with what we've got. And that was all fine. Then along came this guy, Bruno Rossi, an Italian-American astrophysicist. He worked for a private company called American Science and Engineering. They worked on developing new technology and detectors. And it was driving home after one meeting one evening, he had an epiphany. He had a thought that, you know, these soft X-rays coming from these distant cosmic sources, we think they're going to be too faint. But in actual fact, they're going to be traveling right across the cosmos at the speed of light, unimpeded. I think it's worthwhile actually going up there and having a look at them. So one evening at a social function, he bailed up a younger guy, Riccardo Giacconi, also an American-Italian astrophysicist who was only 28 at the time. And he said, look, would you like to, I believe that you're also developing new technology and new detectors and interested in X-ray detection and so on. He said, yeah, that's right. He said, would you like to come and join our team? I want to put a team together and we want to concentrate on this. And so they did. The two of them headed up some teams, and also Riccardo Giacconi is also now considered a father of X-ray astronomy. So these guys got going, but they put their proposal to NASA, and lo and behold, NASA declined them and said, look, why are we going to give you guys money pursuing something that we all know is just fruitless? There's just no point in it. No one believes in it. Go away. So they did go away. So what they did, they had a plan, a cunning plan. So cunning, you put a tail on and call it a weasel, a very cunning tail. What they did is they put a proposal together. There was a crowd called the Lunar and Planetary Exploration Department at an Air Force Cambridge Research Laboratory. And they said, we want to put up some rockets with some X-ray detectors on them, because we want to look at the moon, because quite possibly the moon could be a source of X-rays. You could have solar X-rays that could be scattering off the moon's surface we could detect, or you might get these high energy charged particles coming from the sun, striking the surface, particles on the surface of the moon, which then emit X-rays, and that seemed all pretty good. So they got accepted, they got the funding. And that enabled them to get built for them 4 Arabi 150 rockets. 4 of them, were in 2 stages, and they could go to an altitude of 225 kilometers. In other words, high enough altitude, they could start seeing these soft cosmic X-rays. Instead of having 1 by 1 centimeter little Geiger counters, they put on 3 of them and 10 by 10 centimeter Geiger counters. In other words, Geiger counters 100 times more sensitive. Friedman's his Geiger counters also only had a range of about a field of view of about 3 degrees, not very big in the sky. Suddenly these Geiger counters had field of views 120 degrees, much wider sweep. And that allowed them, for the time that they were going to be in space, usually you're talking sort of 20 or 30 minutes or so with these suborbital rockets, it allowed them to do an in-flight full scan of the sky. And of course, they chose night missions to be close to the full moon, because at the end of the day, that's what they were meant to be doing, observing the moon to get their funding. But also, they didn't want noise. They knew the sun produced X-rays. They'd already discovered that. They didn't want that was extra noise. So they flew their rockets at night time to have a quick look at the moon. And when no one was looking, of course, swung around and had a look at the full sky, trying to see if they could detect any X-rays. And lo and behold, they shocked the Astronomical Society. The whole world was absolutely stunned with what they found. So from the White Sands launching site in New Mexico, 18th of June, 1962, they sent up one of these Arabi, 2-stage Arabi rockets with these 3 Geiger counters on. And here is their results, what they discovered. So up here on the Y-axis, you have the number of counts, the number of X-ray photon counts. And along the bottom here, you've got the degrees across the sky, 0 degrees right to 360, so the full range across the night sky. And they discovered two things which surprised everyone. First of all, you can see this count going right across here. So there was a constant background of X-ray radiation right across the night sky, full 360 degrees, right around. There they had background X-ray radiation, nothing that anyone thought they could ever detect. But look at this, was very, very exciting. A huge peak, something, there was some source out there, and that's in the constellation of Scorpius. There was some sort of source that was giving up high radiation levels in X-ray wavelengths. And I thought, that's interesting. So you've got a big source there, and about 60 degrees, you can see there's another smaller source. So this mission was essentially the birth of X-ray astronomy, 1962. So from then in, they did some further flights, and they, in October 62, they found another localized weak source, as well as confirming the large one in Scorpius. And this was about just close to the Crab Nebula, which is a known supernova remnant. And they found, oh, there's another little localized weak source up there. So they sent up another flight in July 64, and they found that source that they had picked up near the Crab Nebula was actually entire light year in size. So they're starting to determine now how big things were as well. So that was interesting. Not only have we got another source, it's a whopping light year in size, whatever it is that's producing these X-ray wavelength radiation. A balloon flight in 1965 at 15 to 60 kilo electron volts of energies. So that was talking higher, and balloons can do that. They confirmed that this radiation was coming indeed from the Crab Nebula, also known as Messier Object M1, which is, yeah, as I mentioned, is a known supernova remnant. So they're able to confirm pretty much that these supernova remnants did indeed with the source of X-ray radiation. Now, and of course, this is the first supernova remnant seen in X-ray in comparison to that highly detailed one I showed at the beginning. So immediately it was telling them, we can discover new things. With X-ray astronomy, we can learn some new information at things that we knew were already out there. Now, you might question, well, why bother with balloons? We've got X-rays. We've got rockets now that can go up and X-ray in the upper atmosphere and pick up soft X-rays. Why bother with them? Well, balloons obviously can only go up to an altitude. They can only pick up the hard X-rays, but it's important to study them. But the key to balloons, they can stay up a lot longer. They can remain up in the atmosphere up to 100 hours, as opposed to a sounding rocket at high altitude can only stay up there for a few minutes, 18, 20, 25 minutes or so, they come back down again. Balloon can get up there, study the hard X-rays at the low altitudes, but for longer lengths of time, many hours. So there is a role for those balloons as well as these sounding rockets. So let's have a look at some of the further missions. They then started doing sky surveys with a more detailed look at the entire night sky across the galactic plane. And you'll see here, they started realizing there was lots of little sources, and they confirmed that something in the constellation of Scorpius was giving out some pretty intense X-ray. Look at that comparison to these other sources here. And you've probably picked up here how they named their sort of sources of X-ray. So this was called SCO-X1, and that was because it was the first X-ray source discovered in the constellation of Scorpius. They also picked up an interesting one, which we're going to have a look at later on, called Cygnus X1, the first X-ray source in the constellation Cygnus. So we're going to have a interesting look at that later in the talk. So Scorpius X1, you might say, well, gosh, let's just go back. So that was the first source that was picked up, and they confirmed it was pretty high. So what could that have been? So with further missions, they analyzed it further. They then had a closer look at an optical wavelengths to see this is what we can see, some strong X-ray radiation and what else is up there. And they actually found out that it had a red giant going around. So it was a binary star system. There was some object that they were having trouble identifying. It was going round and round in a binary system with a large red giant. Now, what is a binary star system? A lot of stars, like our sun, just goes quietly, merrily on its way through the galaxy on its own. Most stars, however, actually go orbiting the galaxy in a system, in a gravitationally bound with either 1, 2, or 3 or more other companions. And if you get 2 of them going around together, it's called a binary system. And they're quietly gravitationally bound, going around together as they move through the galaxy. They're called binary systems. And they analyzed it further, and they realized what they had was a neutron star. And remember at the start, that first picture I said, a neutron star is the compact, dense, hot object left over from the core that had collapsed in a large star greater than 8 masses. And of course, the rest of the material just gets spewed out to form that supernova remnant. And they then discovered there's a process that's going on. If you get one of these small, compact, very dense neutron stars here, its gravitational field is very strong. And if it's very close to a large red giant star, it siphons off the material from the outside of the red giant. It doesn't fall straight onto the neutron star, but rather forms a disk called an accretion disk around there. And then ultimately, material spirals inward like this, in and in to the inner layers of the accretion disk, and then fall onto the surface of the neutron star. And as material falls from the disk onto the hot neutron star, it loses a lot of gravitational energy as it heads towards the neutron star, and it gives out a lot of energy as it strikes the surface of the neutron star. Both those processes are highly energetic, and they give off X-rays. So you've got X-rays coming from the neutron star, and you saw that in the picture. But if it's in a binary system, you also got X-rays coming off in these inner regions of the accretion disk. And that's what it turned out to be. Now, up till this was 1967, early 1967, neutron stars were just theoretical objects. They thought they probably do exist, and they proved them mathematically. It was a guy called Fritz Zwicky, which we'll talk about at a talk we do later on this year, hopefully next month, on dark matter. And he was a Swiss-American astronomer, well ahead of his time. And in the 1930s, he proposed that these dense, compact objects would be out there, neutron stars. This was the first observational evidence that neutron stars existed. So immediately you can start seeing how the field of X-ray astronomy was just opening up. They were discovering new processes. They were discovering, evidence for new astronomical objects. It was huge. And those of you are aware that if you looked up neutron stars, you'll hear that Jocelyn Bell in 1967 first discovered them by discovering a pulsar, which is a young, rapidly rotating neutron star. Wasn't it Jocelyn Bell? These guys actually bet Jocelyn Bell to the line in terms of finding the first evidence that they did exist. So let's now talk about chapter 3, not the 1970s. So 1960s were these first pioneers. They had their sounding rockets and balloons, and they opened up the whole field, but they were just sounding rockets and balloons. The 1970s herald the age of satellites. And the advantage of a satellite is suddenly you're in Earth orbit, you're not coming down straight away again. And it allowed them to do prolonged observations high up in the atmosphere of these soft cosmic X-rays. And there were 5 dedicated X-ray satellites in the 1970s, namely SAS-1, Oriole 5, SAS-3, HEO-1, and HEO-2, which we're going to have a look at right now. Okay, so SAS-1, also known as Uhuru, it was a NASA project, and that was it was launched in December 1970. It was called Uhuru because it was launched from Kenya. You might say, why launch it from Kenya? It's close to the equator, and you get immediately you've got a bit of velocity because of the Earth's rotation, so you get a bit of a velocity boost to enable you to get into a nice high orbit called a launch assistance. So that's why they launched in Kenya. And as they launched on the Independence Day for Kenya, and Uhuru in Kenyan means freedom. Now, here's a picture of it here, and you can see, look at this here. This is the beautiful instrument. So instead of, you know, a 1 square centimeter or even a 10 by 10 Geiger counter, these guys now had developed the proportional counters, which means they could differentiate between the different energy levels within a certain range of these X-ray photons. But suddenly they had two 840 square centimeter proportional counters, a huge advantage. So these large proportional counters that were obviously now in orbit were ideal for examining closer looks at faint, extended, or complex objects. And this was in the sky for over 2 years. They were able to identify 339 X-ray sources, determine fairly accurately their location, how intense they were, and the variability. And you might say the variability, yeah, that refers to a lot of these X-ray sources just weren't constantly blaring out X-rays. There was a variability. Their X-ray emission was just hovering all over the place. And they thought, what is all this about it? But they recorded it and thought, we got to work this out. Now here you'll see it, there's doing some pre-flight testing at NASA. This is Bruno Rossi, one of the fathers. He was, you know, the guy who first suddenly decided, hey, look, I think it's worth doing. This here is Margaret Townsend. She was, okay, so we're in NASA in the 1960s. And here she is a lady, and she was the project manager for a whole series of NASA satellites. And that in itself was just fantastic. So she was a pioneer engineer, space technology engineer in NASA. And you don't hear her name very often. So I make a plug there for Margaret Townsend. Okay, so let's just have a look at some of the notable observations from Uhuru. There's one called, so I'll put some interesting ones here. Centaurus X3. So in other words, it was the third X-ray source in the constellation of Centaurus. And they found that they found a source that was giving a pulsation of periods of just, you know, just under 5-second pulsations of little bursts of X-rays, but they were superimposed on sort of 2-day fluctuations. So you might get 2 days of these little 5-second fluctuations, and then it dips for a period of time, and then it comes back up again for a prolonged length of time. And these, so we thought, well, why are these getting these 2-day fluctuations with these, you know, sort of just under 5-second pulsations? What's going on? They concluded it was an X-ray pulsar with an occulting binary system. So please explain, I wrote there. So what's going on here? So for starters, you've got a binary system, 2 stars going around one another very closely like that. One of them might be a red giant, but in particular, we talked about the neutron stars, these compact dense things, which you've now seen in that first image. So they worked out that one of them was a neutron star, the other one was a supergiant. How do they know that? They swing their normal telescopes and have a look at the site where these bright X-ray pulsations are coming from. Now, this neutron star was called a magnetar. So what's a magnetar? A magnetar is a young neutron star that's rotating very, very quickly, and it's got very intense magnetic fields around it. So there it is spinning around with its supergiant to one side. It was siphoning off material from the nearby supergiant, but instead of material falling into an accretion disk that just gently falls onto the surface, like that previous one with Scorpius X1, suddenly it gets into the accretion disk, but as it falls, you've got this magnetar's got these intense magnetic field lines that then direct the inner accretion material, directs it along the field lines and directs it straight to the poles. So you get here, instead of falling onto the surface, instead it gets directed down the magnetic fields, down to the hot surface of the neutron star, right on these poles of the magnetic axis. Much like the auroras, very similar principle that we see with the northern southern lights here, except this is where the charged particles from the accretion disk get directed down to the hot surface, and from them X-rays get emitted, and the X-rays get emitted from these magnetic poles of this rapidly rotating neutron star or magnetar. And it so happens that if the magnetic pole axis is not in alignment with the rotational axis of the neutron star. So that's its rotational axis, and it's spinning like that, but its magnetic axis is pointing out like that. And with the X-rays splurting out in those angles, you are going to get a wide sweeping, like a lighthouse, sweeping around and around of these X-ray emissions. And if we happen to be in the line of sight of one of them, what we see is these quick pulsations, flashes of X-rays coming at us. And exactly the same analogy as a lighthouse. A lighthouse has its light beam spinning round and round. And if you happen to be looking at its line of sight of that beam, all you see as the observer is this flash of light coming at you at regular intervals. And this is exactly the same principle. Most of you have probably heard the idea of pulsars in terms of radio pulses, radio signals getting sweeping across the sky that you pick up as radio pulses. Exactly the same here, except these are X-ray pulses. So instead of a neutron star just on its own giving out radio frequencies, this time they've got this magnetar, young neutron star, highly magnetic fields, happens to be close to a supergiant, siphoning the material off. Lots of material being dragged down to the surface, the magnetic poles, and causing X-rays. So really, really interesting stuff. You might say, well, okay, I get that, why the 4.84 second pulsations, but how about these 2-day fluctuations? What's that about? That is because they're part of an occulting binary system. And occulting means when one blocks our view from Earth of the other one as they go around. So the whole system is being blocked as the supergiant heads in front of Earth and blocks out our view of the pulsar, in particular of the X-ray radiation sweeping across the sky. So that was something totally new that they had to work out was going on. Why? Because of X-ray astronomy. They then swung around with these X-ray satellites and started looking at galaxy clusters, these gravitationally bound groups of galaxies. And they started picking up these hot gases we talked about earlier on. There's these hot gases in there through that Bremsstrahlung radiation. And they noticed that there's a lot of hot gases swarming around these big clusters. And the temperature of the gas, in this was the coma cluster, was, so we're talking 7.3 times 10 to the 7. So what's that? So, 73 million degrees. So that's hot, hot, hot. So what do you need to hold something that's flying around so quickly, to hold it together? You need gravity and mass to hold that together. And they soon worked out that because the gas was so hot that they could obviously pick up because of the X-ray radiation, they could now detect it. They realized there wasn't enough mass for the matter, what they could see visually through optical wavelengths, visible wavelengths, to account for the mass that had to be there to hold these high energy, high temperature gases together. And that was another argument for the fact that there was something out there unseen called dark matter. So another strong observational evidence. They didn't really have this sort of backup until X-ray astronomy. Another one, this Cygnus X1 that I mentioned about. So here we go, is they started noting, once again, X-ray source that was pulsating, very, very short durations, about 1 second or so, and there were no stable periods longer than about 10 seconds. So just quick bursts of X-rays fluctuating. Something is going on here. And there's a principle in astronomy: when you see something, radiation, electromagnetic radiation or light, coming at you in small pulsations like that, the object or source of those pulsations cannot be larger, its diameter cannot be bigger or larger than the distance that it takes light to speed in those pulsations, because it takes time for it to fly across. And that short space of time told them that those rapid variations indicate that small source was very, very small, smaller than the size of Earth. So something really small and compact out there was pumping out these quick, rapid bursts of X-ray radiation. So they looked at that same source, that where it was coming from, with the optical telescopes, and they saw there's a big blue supergiant star there. Once again, this was a binary system going on with your big supergiant companion. and it was obviously dragging material from it. Once again, here it is here, dragging material. Here's your supergiant, dragging material onto some compact object. An accretion disk was forming and emitting X-rays that was falling in, and that's obviously what they were seeing. Now, there's another principle in astronomy. If you get two objects going around one another, and you can easily just observe and record the period, how long it takes them to go around one another, and you happen to know the mass of one of them, which they could easily identify with a supergiant, you can very quickly work out the mass of the second object. And they worked it out, and they realized the second object, the invisible one that they couldn't see anything there, but that had a mass greater than 10 solar masses. In other words, it had a mass greater than 10 times the mass of our sun. So it was a pretty massive object, but they knew it was smaller than the size of the Earth, and they couldn't see anything. There was only one thing it could be: a black hole, a stellar black hole. And this, guys, was the very, very first observational evidence that black holes existed. So you've already seen the X-ray astronomy opened up this whole field of astronomy. Suddenly they could see these sources, they could see a background was going on, they could identify, they had proof now that neutron stars existed, and they now had observational evidence that black holes existed, all because of X-ray astronomy. They also were able to, this background radiation, this graph is one of what they call a Seyfert galaxy, which means that a Seyfert galaxy is a very large active galaxy, which means it's got most large galaxies have a supermassive black hole in the middle. Milky Way's got one too. But a lot of those galaxies, those supermassive black holes, have material in and around the region. And just like with those compact objects, they get an accretion disk, accretion matter falls into the supermassive black hole, and in the process of that loss of gravitational energy, high energy X-rays get emitted. And you've got a lot of galaxies out there in the distant universe, these big Seyfert active galaxies, big active supermassive black holes blazing away. And they were able to determine that certainly at least a quarter of all this diffuse background was certainly at least a quarter of it was coming from these active galaxies way in the distant universe. Here's a shot here, another one in X-ray. Here's a Seyfert active galaxy here. Look at all these hot gases, big bubbles of gases that are being given away. And that's because particles are being shot out into outer space and heating up the molecules and the particles that are in the space between the galaxy. Here's a galaxy here. Look at the size of these bubbles, huge. And once again, this is all because of X-ray astronomy. So we'll go through briefly some of the other ones here. There's the Oriole 5 satellites. That was a joint mission between the NASA and the British. Here, suddenly, and this is a common theme with each mission, as you're starting to see, and you continue to see as I go over some of the other missions here, they were all getting more instruments, more versatile instruments, able to look at different things. The instruments were getting more sophisticated, and more precision astronomy was occurring. Here, and I put it's in small print, but you can go back over and look this later if you're interested. Collimators able to help with direction, find out exactly locations where a source might be coming from. Spectrographs, high resolution, trying to determine if some of these X-ray emissions is polarized, which is very important with that synchrotron radiation, charged particles going magnetic fields, and so on. So each instrument was more instruments, more versatility, more sophistication, and more precise measurements. And that's a common theme with all these. They were able, for example, to work out what's going on. They're called cataclysmic variables. And that's where you get these suddenly big bursts of X-rays going on. And they were able to determine that these, once again, another form of compact object called white dwarfs. And that's the stellar remnant of stars less than 80 solar masses. And if they're in a binary system with a red giant, you get the siphoning of material, the accretion disk, but the matter falls onto the surface of the white dwarf. It's not strong enough in a neutron star or black hole to emit X-rays, but what happens is the hydrogen builds up on the surface of the white dwarf until it reaches a critical temperature, a critical pressure, and nuclear fusion in a runaway fashion just goes poof, and the outer layers of the white dwarf explode and emit a lot of X-rays. and the star survives, or the white dwarf, I should say, survives, and the process tends to repeat itself. But once again, the X-ray astronomy was able to give them better ideas of what was going on with these processes. They were able to see that Hercules X1 was an interesting object. They were picked up here, whereby there was sort of a lot of uncertain sort of changes going on. They couldn't quite understand why they were getting certain types of X-ray fluctuations. And slowly they studied it in X-rays. And what it did do, it showed the variability was because of changes within the flow. As the material gets sort of near the inner regions of these accretion disks, they go faster and faster and faster. And the flow patterns get more and more complex, and they start just causing variability and fluctuations in the X-ray emission. So essentially, X-ray astronomy was now allowing astronomers to get a better understanding of the complex processes that are occurring in these accretion disks around these black holes, neutron stars, white dwarfs. Then there was the SAS-3 satellite. Once again, and more improvements in the instruments. Suddenly the timing for these fluctuations in X-rays, they were improving to 1 part in 10 billion rather. So really, really fine little time frames they were able to work out the fluctuations. They had more, suddenly they were working on the satellites. The satellites themselves in the past might have been a little bit wobbly and only so accurate. Suddenly they had developed the technology to stabilize the spin and control of their satellites. That, with better timing accuracy, they could get a better idea of exact, precise locations and fluctuating X-ray events going on. And they could do it throughout the whole year through these satellites. So you get the gist of it. The technology was getting better and better, more and more refined, more and more information of these high energy events going on in the sky. More highlights. Okay, quasars are very, very bright. They're essentially active galaxies, but big, powerful beasts from the early galaxies in the universe. Very powerful, and they were the first. This was the first satellite to pick up quasars emitting in the X-rays. They were also were able to observe a lot of stellar flares from the sun, have a closer look at it, and they were able to identify also X-ray flares coming from individual stars. Okay, they were able to note X-ray bursts coming from the center of our galaxies, which gave them a lot of information. That's an area that's hard to look at with your normal telescopes, because you've got to look through to the center of the galaxy, a lot of dust and so on to look at. They were able to get a clear view in X-ray and see some of the high energy processes that are going on in the center of the Milky Way. Normally that's out of view. Okay, then NASA started developing these much larger ones. They called them High Energy Astronomy Observatory 1 and 2. And these things flew in the late 70s. And look at the size. Here's a technician in here. So suddenly, you remember that one I showed you with Margaret Townsend and Bruno Rossi? You know, that they were as big, the machine was about the same size as them, a little bit bigger. Look at the size of them. And this was a huge jump in the size and the technology and the size of the satellites. So this time at the proportional counter, you had a 1 square meter array of proportional counters. So suddenly they were able to get up there and do more detailed catalogs. In other words, look at every object they could and catalog where they were in the sky and get much more better detailed accounts of those sources. The interesting one, so that was the HEO-1, but I'm moving straight ahead to the most interesting of the lot. And this was the HEO number 2, and it was launched in 1978. And as soon as it was launched, they left the launch pad, they quickly renamed it the Einstein Observatory. They just wanted to make sure it got up there successfully first. And it was the first fully imaging X-ray telescope. Up till now, there's been Geiger and proportional counters, just counting photons. But suddenly they could get a telescope up there. And you might say, well, hang on a minute, didn't you tell us if you get a telescope with mirrors and stuff, the X-rays are so powerful, they can just go straight through them? Well, here's a very cunning plan. So it's called a Walter Type 1 telescope optical design. This is not to scale. So I drew this up. It was just really to explain the principle first, and then we'll have a look at a scaled picture of one. So they put a couple of pairs of mirrors. So you have a pair here called parabolic mirrors and then a slightly different angle called hyperbolic mirrors here, and the central focal point is here. So the idea is that photons come in, these high energy X-ray photons come in at grazing angles, not straight on, but grazing angles, get reflected to another mirror and then down to the focal point. So they're able to capture and focus, forms of mirrors to capture and focus these high energy photons that would normally just go plow straight through a mirror. So the next question you might say, but isn't that a pretty inefficient way of collecting photons? You know, pity you can't just have a mirror like that. You're set, you can't do it. But jeepers, it's a lot more efficient than having something at a grazing angle. So what they do is they create nests of mirrors, concentrically arranged sort of sets of mirrors. And the Einstein telescope had these 4 sets of mirrors, all just beautifully all nested here together. So the photons come in, get grazing angles and get reflected to focal point, but you've got nests of mirrors going on. This whole thing was put together and designed by another sort of giant, the 4th person I want to introduce tonight, Leon van Speyebroek, and he was a Dutch scientist, and he was considered the premier X-ray telescope mirror designer, responsible for developing the Einstein and the Chandra X-ray observatory mirror systems. And it's the same system that he developed for the Einstein one that got put into the Chandra X-ray observatory, which was launched in 1999 by NASA and is still operating to this day. And it was responsible for that lovely image of Cassiopeia A supernova remnant right at the beginning of my talk. So as you can see here, it's just suddenly this telescope just didn't have mirrors up there. It had an array of multiple instruments with much more improved resolution and sensitivity, 100 times more than any previous mission. So this was a huge technical milestone in X-ray observations. So I'll just go through. They did a whole lot of highlights as well. They were able to do X-ray missions from 143 stars at different evolutionary states. And what they were able to pick up, that stars actually emit more X-rays than the models at the time of stellar evolution suggested, which really mean that the guys had to go back and review and refine their models of how stars evolve. But it also indicated that a lot of just simple stars on their own, just blazing away in X-ray, also contribute a reasonable amount to that background galactic sort of X-ray emission they picked up. You saw from that earlier picture that I showed you at the beginning of the talk, all the fine details and intricate structure within a supernova remnant. Well, it was the Einstein Observatory that was first able to pick up this sort of detail and do nice little maps of the shock waves coming out, which indicates the amount of material, the direction the material is going in, and its velocity in different directions. So they were able to do that. They were able to do models from there, because they could tell what sort of energy we're giving out, which indicates what sort of elements are being formed. So that helped improve models of what elements are being formed inside massive stars and during the supernova explosion. So from here, moving along, the 1980s, as you saw, the 60s and 70s was pretty much essentially all NASA American stuff. The 1980s was dominated by further more advanced X-ray observations, satellites by the Europeans and by the Japanese. And then the 1990s, there was a few, but in particular 2 very, very important X-ray observatories were launched, namely the Chandra from the NASA and the XMM Newton Observatory from the Europeans. We'll briefly look at these guys just to show them off. So that was the picture that we saw earlier on, the picture of the Chandra. That is a beautiful telescope. I think that would have to rate as one of my most favorite telescopes. So this is what it looked like here with the Chandra has a nest here. It's what of 4 mirrors all nested together. Here it is, the grazing angle, and it was able to be focused down there. So there was precision polish, and it's all about, because you're talking really fine, low wavelength photons. So, which means you had to be very, very precise to get nice definition. So precision polished for 84 centimeter long concentric nestled mirrors, 2 centimeters thick. And they were very thermally stable. And that gave a high resolution pictures of up to 0.5 an arc second. So that's pretty high resolution over 30 arc minute field of vision. So that essentially, never mind the figures, is telling you they can take very precise assessments and images of objects in fine detail over wide ranges. The Cassiopeia A, the very first one I put up that I highlighted, illustrates what the Chandra could do. So how about the XMM Newton Observatory that was launched by the Europeans in 1999? It was actually 3 telescopes rolled into one, and each telescope had 58 gold-plated nested mirror pairs. 58 pairs of mirrors, and that 3 of them within the whole observatory. And it gave a total collecting area, and I think my slides are a little bit obscured. From the top of my head, I think it was something like what I've written there, I can't see it. It was 84 square meters of total availability of surface area to collect X-ray photons. So check that out. You can see it was just advancing as they were realized the importance of X-ray astronomy, what they would find out. It suddenly motivated them to develop the technology more and more and more. And really, astronomy has gone ahead leaps and bounds over the decades because of X-ray astronomy, and in particular of these 4 giants who I'm going to recap shortly, these pioneers. So we're now on to the summary. So let's have a look. These pioneers, I don't expect you to remember their names, but at least recognize their names if you see them again. I love that saying, born on the breeze and die on the wind. So if anyone can tell me what song from the 1970s did that lyric line come from, you'll get a virtual chocolate egg, chocolate or chocolate fish or something like that. I'll give you a clue. It's from the 1970s and the artist is still standing. Okay, so we had Herbert Friedman, 1950s, developed those sounding rockets. Bruno Rossi, who's the first guy who had the insight to realize that it actually is looking for these soft X-rays. Riccardo Giacconi was the main sort of technical guy who got it all going, and then he supervised pretty much all those 1960s sounding flights, and he supervised most of the satellite missions in the 1970s. Leon van Spaebroek, he was the Grand Master who first came up and designed these mirrors, these Walter Type 1A mirrors that were able to capture X-ray photons with this clever design and enable the sort of increase the resolution in the images they could get. Just the historical X-ray observatories over these 2 crucial decades. The big one was that 1962 in June, that initial sounding rocket that galvanized the X-ray community, the X-ray astronomy community. The 1970s, we saw 5 satellites, each getting more and more advanced, allowing prolonged and more precise observations of these sources of X-ray emission. The main discoveries, of course, initial one in 1962 showed there was a constant background of X-ray emission right across the sky. And amongst there was peaks, in particular that one was at Scorpius, was a huge big peak, but it showed it was worthwhile getting up there and exploring X-ray astronomy. And the 1970 satellites then showed the evidence for these 3 main compact, hot, dense cores, sort of stellar corpses, if you will, from after stars have spent their lives, white dwarfs, neutron stars, and black holes, in particular how they behave when they're in a binary system with a red dwarf, or sorry, with a red giant rather. It picked up hot gases between the galaxies within galaxy clusters, giving evidence for dark matter. They were able to see a lot of diffuse background radiation and where it was coming from. They concluded a lot of it comes from these active galactic nuclei, in other words, these active supermassive black holes at the center of galaxies, and the big brother beasts of those AGNs called quasars. They were able to get more precise catalogues of all the sources of X-rays across the sky. And as you saw right from the initial slide I showed you, they were able to study supernova remnant structure a lot more finer and work out what sort of elements had been formed in that initial supernova explosion. So you'll see here how there was 4 very, very clever people who got this all off the ground. The history of X-ray astronomy in the 60s and 70s is important. It's rich. So I hope you've enjoyed watching the history and importance of X-ray astronomy and taken some messages away, and sort of you've learned about the pioneers, the missions, and their discoveries. So thank you, everyone. Now, James or Josh, you want to come on? Because I think we can have some time for some questions.
Yeah, so I've got a couple of questions here. First one's from Ben.
Hello, Ben.
He says, how long do the X-ray bursts from the white dwarfs last? In terms of measurement window for the satellite instruments, is it nanoseconds or is it days?
Oh, okay. I think you're looking at. I think you're more looking at sort of hours towards a day or so, because it takes a while for the emission to go back down again. So it's most intense over a few hours, and it might take a day or two just to quietly settle back down again. And there was a recent study that came out last year, and I think it was from a New Zealand astronomer was involved in it, how they were able also to detect a lot of light and visual wavelengths as well with the X-rays, and the understanding of it has improved a heck of a lot even within the last year or so. But in answer to you, Ben, you're talking in hours.
Okay. So the next question is from John Burkett.
Hi, John. Hi, John.
He says, with X-ray emissions coming from the poles of the magnetar, if the poles are pointing perfectly away from the Earth, can we still detect the X-rays, or do they need to be towards us?
They need to be, our line of sight needs to be within somewhere in the line where the X-rays are sweeping the sky. If we are not in the line of sight at any stage, with that beam does not cross over in the line of sight between the magnetar and Earth, we don't see it. So there are loads of pulses out there that are emitting an X-ray, or more commonly in radio wavelengths, that we're totally unaware of. We just see them as neutron stars, because the emission from the magnetic pole may not be sweeping. So we've got to be in the path of that sweep of X-ray emission for us to see those little bursts.
Okay.
And I suppose a good one, like the lighthouse scenario. So I can look straight out of my office window right now and I can see the Terry Lighthouse bleeping, and I just see it as a quick burst like that. But if I was up much higher and out of the line of, where it sweeps around, I wouldn't see it at all. I wouldn't see that. I might just during the daylight see, there's a big white tall building sitting there. So that gives you an idea of that. We've got to be in the line of path of the sweeping path, somewhere in that sweeping path for us to see it, else we wouldn't see it as a pulsar.
Okay, and Ben says if the artist is still standing, it's got to be Elton John.
You got it, Ben. Okay, come along to the next meeting, Ben. I'm sure we'll have some sort of chocolate delight for you, possibly an egg, or a chocolate egg, or a chocolate fish, or something. Well done. It was Elton John. It was this song has no title, and it was it was called it's of Yellow Brick Road, Grey Seal rather. The song Grey Seal, track 3, Yellow Brick Road by Elton John, lyrics by Bernie Taupin. Born on the breeze and die on the wind. I love it, and that's what all these guys, these pioneers, were about.
And Sandra says she loves your shirt.
Oh, thank you. My Hawaiian shirt, yeah. I thought summertime, be a little bit more casual and relaxed. The picture here is not of my cat Stella, but looks like my cat Stella, and pretty much typifies Stella's eating habits.
Okay, just having a look. There we go, that's a bit better. So are there any other questions out there? I know there's a little bit of a delay.
In the meantime, I might as well get a plug-in for our mugs. You two guys can have a fancy mug like this. Come along to our meetings. Red Beach, the first and third Thursday of each month, 7:30. Get yourself a mug. Be cool. Hang out with the cool guys.
They're really good mugs, I must say. It doesn't look like there's
any, we're all good.
Any others on there. So let me just. I'm changing something over here.
Well, in the meantime, I'll say, look, thanks, guys, for joining in, and hopefully we'll be, hopefully we'll get sort of back to physical meetings as soon as we can. But it's a bit of fun in the meantime doing an online one. So thanks for joining us.
Thanks a lot, everyone, for
Be safe.
attending. It was really great. If you want to hear Josh's music, I've put a link to his SoundCloud in the Facebook group, so you can go and have a listen to that and give some feedback on that. Anyway, thanks very much, everyone. I hope you have a very good evening, and keep an eye on the Facebook group and the email for the next meeting, which will probably be in person. And at this stage, we are possibly having a guest speaker as well, so something to look forward to. So thanks a lot, guys.